Welcome to this practical lesson on electrolysis, using inert electrodes. We're about to step into the lab to explore the process of electrolysis. Specifically, we will look at what happens when we electrolyze different aqueous solutions using inert electrodes. Before we begin, over to Sam, our lab technician, to outline what safety equipment we need.
Hi everyone, I'm Sam. Before we get started, make sure to put on your lab coat, safety goggles and gloves. Safety first in all our chemical explorations.
Thanks, Sam! As we prep for this practical, let's quickly recall what we've learned so far. We've delved into the principles of electrolysis, understanding how an electrical current can drive non-spontaneous chemical reactions. We've also discussed the role of electrodes, both inert and reactive, and how they participate in or facilitate these reactions. Recall that reactive electrodes are those that actively participate in the chemical reaction, whereas inert electrodes are those that do not actively participate. Today, we're going to test a specific hypothesis. Oxygen is produced at the positive electrode in electrolysis of an aqueous solution unless the compound contains halide ions. To do this, we'll set up an experiment where we electrolyze various aqueous solutions and observe the products at the inert electrodes. We're almost ready to dive into the details of the practical, but let's quickly explore why this experiment is useful. First, let's discuss the industrial and practical relevance. Electrolysis is a crucial process in many industrial applications, from the extraction of metals to the production of chemicals like chlorine and hydrogen. By understanding what happens during electrolysis, we gain insights into processes that are vital for manufacturing, energy storage, and even wastewater treatment. Secondly, this practical gives you the opportunity to engage in hypothesis testing, one of the fundamental aspects of scientific inquiry. By carefully observing the products formed at each electrode, we can evaluate whether our hypothesis holds true across different solutions, deepening our understanding of electrochemical principles. Finally, conducting this experiment will help you develop key laboratory skills, such as setting up an electrolytic cell, making precise observations, and conducting tests to identify unknown products. These skills are essential for anyone pursuing a career in chemistry or related sciences. On to the practical. Let's start by gathering our materials. Sam, what do we need?
So, for this practical, we need beakers for different aqueous solutions, 2 graphite electrodes, a 12-volt DC power supply unit, test tubes to collect gases at each electrode, a pair of tongs for safely handling the electrodes, litmus paper, splints, and iodine solution for testing the identity of gases produced, and, finally, a lab book to record our results. We also need to ensure we have all the aqueous solutions needed for this experiment. Today, we'll use copper chloride, calcium nitrate, silver sulfate, potassium bromide, sodium iodide, and sulfuric acid.
On to the practical. Start by filling the beaker with one of the aqueous solutions. We'll start with copper chloride. This will serve as our electrolyte. Then, insert the 2 graphite electrodes into the solution, making sure they are not touching each other. Connect the electrodes to the power supply, with one electrode connected to the positive terminal, making it the anode, and the other to the negative terminal, making it the cathode. Graphite is used because it is an inert material. It does not participate in the chemical reactions taking place in the electrolyte. This ensures that the only reactions occurring are those driven by the electrolysis process, leading to accurate results without interference from the electrodes themselves. Next, we need to fill the test tubes with the same electrolyte solution, in this case, copper chloride, and invert them over each electrode, ensuring that no air is trapped inside. This setup will allow you to collect the gases produced during the electrolysis process. Now, we turn on the power supply and observe the reactions taking place at each electrode. After a short time, you should see bubbles forming at one or both electrodes, indicating gas production. These gases will be collected in the inverted test tubes. Run the experiment for only about 2 to 3 minutes, as this should be sufficient to see the reaction progressing and collect enough gas for testing. Extending the duration could lead to side reactions or the buildup of unwanted byproducts, which might complicate the interpretation of results. After we have observed the reaction, we need to record our observations so that we can later identify the products that have formed. In your lab books, carefully draw out a table within which you can record the observations at both the cathode and the anode, as well as room for further notes when we conduct tests to identify the products formed. In the case of copper 2 chloride, we will observe a red-brown solid at the cathode and a colorless gas at the anode. Record this in your table. After we have recorded our observations, we need to identify the products formed. Once we have recorded whether a solid, liquid, or gas has been produced, we can select a method to identify what specific product this is. If a solid is formed, we can identify it by its appearance, so there are no further tests required. For solutions and gases, we can run further tests to confirm their identity. We'll now take a brief look at each of the tests we need to conduct to identify the products. If a brown solution forms, add a few drops of starch solution and observe if any color change occurs. If it turns blue-black, then this confirms the solution is iodine. If a yellow-orange solution forms, dip damp litmus paper into it. If it bleaches, then it is bromine. For the gas collected at the cathode, bring a burning splint near the mouth of the test tube and observe what happens. If a squeaky pop is heard, then the gas is hydrogen. For the gas collected at the anode, insert a glowing splint into the test tube and observe whether it relights. If it relights, then the gas is oxygen. If it doesn't, then insert damp litmus paper. If it bleaches, then the gas is chlorine. All of these tests used to identify the products formed during this experiment are summarized in this table. Now that we have run through the tests required to identify the products, we can go back to filling in our results table. In the case of copper chloride, we can identify the solid formed at the cathode by its red-brown color as copper. The gas formed at the anode doesn't relight a lit splint, but it does bleach litmus paper. Hence, it must be chlorine. We now need to repeat this process for each of the solutions and record our observations. Once you have repeated the experiment for all the solutions, recorded the observations, and conducted further tests to identify which products are formed, you will end up with a table like this. For calcium nitrate, potassium bromide, sodium iodide, and sulfuric acid, a colorless gas was observed at the cathode. To identify this gas, a burning splint was brought near it, and a squeaky pop sound was heard. This sound is characteristic of hydrogen gas, confirming that hydrogen was produced. For silver sulfate, a grey solid appeared at the cathode. Silver ions are reduced to form silver metal, so the grey solid is identified as silver. For calcium nitrate, silver sulfate, and sulfuric acid, a colorless gas was observed at the anode, which relit a glowing splint. Therefore, the gas produced at these anodes was oxygen. For potassium bromide, a yellow-orange solution formed at the anode that bleached damp litmus paper. The yellow-orange color and the bleaching of damp litmus paper confirms it is bromine. Finally, for sodium iodide, a brown solution appeared at the anode, which turns blue-black on the addition of starch. Hence, it is iodine. Now, it is time to return to our original hypothesis. Our hypothesis states that oxygen is produced at the positive electrode in the electrolysis of an aqueous solution, unless the compound contains halide ions. In our observations, we saw that for solutions without halide ions, calcium nitrate, silver sulfate, sulfuric acid oxygen was produced at the anode. However, copper chloride, potassium bromide, and sodium iodide, which are solutions containing halide ions, produce halogens such as chlorine, bromine, and iodine, instead of oxygen. Therefore, the hypothesis was correct. Oxygen was indeed produced at the anode in the absence of halide ions, while halogens were produced when halide ions were present. In this lesson, we investigated the electrolysis of various aqueous solutions using inert electrodes and tested the hypothesis about oxygen production at the anode. Our results confirmed that oxygen is produced unless the solution contains halide ions, in which case halogens are released instead. By carefully testing and analyzing the products, we solidified our understanding of electrolysis. Keep these insights in mind for future experiments and continue exploring the fascinating processes in chemistry.